Morning students, today I am going to discuss about the volume expansivity as well as isothermal compressibility. Volume expansivity, volume expansivity and isothermal compressibility. Volume expansivity and isothermal compressibility. Before entering into this discussion, liquids and gases. In general, on heating, both are tends to expand. On heating, both are tends to expand. Expansion means increase in volume. Increase in volume. On heating, both liquids and gases tends to expand. Expansion means increase in volume. The increase in volume of gases much more greater than that of increase in volume of liquids. Increase in volume of gases is much more greater than that of increase in volume of liquids upon addition of heat. Here, right. Now I am going to check the increase in volume through measurable thermodynamic property. That means volume expansivity. Volume expansivity. The beta notation for volume expansivity is beta. Volume expansivity beta is nothing but increase in volume upon increase in temperature at constant pressure per unit volume of the substance. Clear? Increase in volume on increase in temperature at constant pressure per unit volume of the substance. The notation for volume expansivity is beta. Clear? Sir. For 1 mole of an ideal gas, for 1 mole of an ideal gas, P V is equal to R into T. V is equal to R into T. V is equal to R T divided by P. Here, differentiation on both sides at constant temperature and constant pressure. So dV is equal to R by P into dt. Hence dV by dt is equal to R by P. Now I am going to substitute R by P instead of dV by dt here. This is differentiation on both sides at constant pressure. Hence dV by dt at constant pressure. Clear? So volume expansivity beta is equal to 1 by V into dV by dt at constant pressure. R by P. R by P. Clear? Finally, beta is equal to R divided by PG. PV is equal to R into T, PV by R is equal to PV by R is equal to T or R divided by PV is equal to 1 by P. Hence, beta volume expansivity is inverse of temperature for an ideal gas. The dimension for beta is E inverse. Here, for an ideal gas, volume expansivity is nothing but 1 by temperature for an ideal gas. Next, isothermal compressibility. Isothermal compressibility. Again, the liquids and the gases. Upon compression at constant temperature, the decrease in volume of gas, is much more greater than that of decrease in volume of liquids. Clear? So, volume of gas by compression, volume of gas is much more greater than that of volume of liquids. Volume of gas decreased. Upon compression. Volume of gas decreased on compression is much more greater than that of volume of liquid decreased on compression. Clear? To understand this, the important thermodynamic property is isothermal compressibility. Fortunately, this is also measurable. The notation for isothermal compressibility is kappa K. Kappa K. Clear? It is defined as kappa K is equal to minus 1 by V dV by dP at constant temperature. That means decrease, minus sign indicates decrease in volume with increase in pressure at constant temperature per unit volume of the substance. Volume, that means isothermal compressibility. Isothermal means temperature is constant. Kappa isothermal compressibility. The notation for isothermal compressibility is kappa. It is defined as decrease in volume with increase in pressure at constant temperature for unit volume of the substance. Again, for an ideal gas, 1 mole of an ideal gas, PV is equal to R T. V is equal to RT divided by 1 by P. V is equal to RT into 1 by P. Now I am going to differentiate on both sides at constant temperature. Differentiation on both sides at the constant temperature. So dV is equal to R into T, P power minus 1 into dP. Here, x to the power n into Tn dx is equal to n into x to the power n minus 1. Hence, dV is equal to R into T into minus 1 P power minus 2. Okay, clear? So into dP. So dV by dP is equal to RT divided by P square minus. Now I am going to substitute this one into here. dV by dP is equal to minus RT by P square. I am going to substitute here. This is differentiation on both sides at constant temperature. Hence I am going to put dV by dP at constant temperature. Okay. Kappa K is equal to minus 1 by V into minus of R T by P square. Minus gets cancelled. So K is equal to R T divided by PV into 1 by P. RT by PV is equal to 1. PV by RT is equal to 1. Hence K is equal to 1 by P for an ideal gas. Isothermal compressibility is nothing but 1 by P. The dimension for isothermal compressibility is P power minus 1. Here, students, the important point is both liquids and gases are tends to expand upon heating. Expansion means increase in volume. The increase in volume of gases upon expansion or on expansion is much more greater than that of increase in volume of liquids. This is accompanied by the important thermodynamic property volume expansivity. Fortunately, this is a measurable property. This is volume expansivity or coefficient of volume expansion. Coefficient of volume expansion. Volume expansion. Clear? For an ideal gas, beta volume expansivity is equal to 1 by T. The dimension for volume expansivity is T to the power of minus 1. Coming to the point of isothermal compressibility. Isothermal compressibility. Upon compression or by compression, both liquids and gases decreases its volume. The decrease in volume of a gas by compression is much more greater than that of decrease in volume of liquid. This phenomena is described by the important thermodynamic property isothermal compressibility. Fortunately, this is a measurable property. For an ideal gas, the isothermal compressibility is equal to minus 1 by V into dP by dT at constant temperature. That means K is nothing but decrease in volume with increase in pressure at constant temperature for unit volume of the substance. For an ideal gas, isothermal compressibility kappa K is nothing but 1 by P. 1 by P. The dimension is minus P power minus 1. The another name of isothermal compressibility is coefficient of isothermal compression. Coefficient of isothermal compression. Clear? Thank you.